Hi Math 1025 pre-calculus students. This is a video on section 5.1, much of section 5.1 and some of the skills that you'll need for chapter 5 as well. I ask that since we got snowed out today, you read section 5.1 carefully, you watch this video in whichever order you'd like, and then you should begin the chapter 12, or the homework 12 Wiley assignment on section 5.1 and chapter 5 skills. The first thing that I want to say to start this video is that you need to think of a logarithm as an exponent. That's important, and I'll keep referring back to that. A logarithm is an exponent, and that goes for natural logs as well. All right, and so with that in mind, if a logarithm is an exponent, and we want to rewrite using exponents, okay, if we want to rewrite the log of 11 is equal to x, then we would say 10 raised to the x is equal to 11. So think about this. If we say that the log of 11 is x, and we are thinking that a logarithm is an exponent, then the log of 11, the logarithm of 11, is the exponent. If the logarithm of 11 is x, x becomes our exponent, and our base here is 10. Now, generally speaking, that 10 will not be written, but what I like to do, just to kind of point this out real quick, is I'm going to take that often unwritten base, and that base raised to this power. Remember, this is an exponent. The log of a number is an exponent, so x is the exponent. 10 raised to this power is equal to whatever falls here. So 10 to the x is equal to 11 is equivalent, that's an equivalent statement to saying the log base 10 of 11 equals x, or the log of 11 equals x. Maybe pause the video and try these other three. Okay, so if we say the log of 57 is x, again, the log of 57 is x, means that x is our exponent. We would say that 10 raised to the x is equal to 57. In other words, if you were to punch this into your calculator, you would get an approximation out. You get some number out to approximate x. And whatever 10 raised to whatever that approximation is, or the exact value I should say, 10 raised to whatever that number is, will give you 57. So by saying the log of 57 is x, we're saying what is the exponent that we would have to raise 10 to in order to get 57. So this is the alternate way to write that, just as this was the alternate way to write the first statement. Now, when working with natural logs, your base is e. Generally speaking, it will not be written, so it will actually show up as natural log of 4, not natural log base e of 4. So we have the natural log of 4 is x, and I want to rewrite that using exponents. I would say e to the x is equal to 4. In other words, whatever this approximation is, if you were to punch this into your calculator, whatever comes out, that is the exponent that you would raise e to in order to get 4. Try it. Rewrite the natural log of e squared is equal to x. Again, our unwritten base is e. It won't be written generally. And so we say e raised to the exponent x, e raised to the x is equal to e squared. Now, this is the first time out of these 4 examples that we can say with certainty that x is going to have to be a whole number. In this case, x is 2. The only way I can get e to the x to equal e squared is if x is 2. In the other examples, we would have to round, and we could find that value by punching this in. Okay, I wouldn't have to round, I shouldn't say, but if I wanted to find, I could find an approximation for those numbers. All right, let's take it a step further. Let's jump over here. So the log of x is equal to 2. Notice that our independent, our unknown, I should say, shows up in a different location, whereas in the previous examples, the unknown was over here. Now the unknown is here. So we want to start by rewriting. Well, I'll rewrite this as 10 squared is equal to x. So pause and think about that for just a moment. Here's your unwritten base of 10. 10 raised to whatever shows up over here equates to whatever's here. So 10 squared is x, so we can say with confidence that x is 100. And you could check by typing your answer in and say, what's the log of 100? The log of 100 is going to come out to be 2. Not sure what happened there. 2. There we go. The log of quantity x minus 4 is equal to negative 3. an alternate way to write that would be 10 to the negative third is equal to x minus 4. Well, remember, I don't have a ton of space here, but remember 10 to the negative third is the same as 1 over 10 to the third. 1 over 10 to the positive third. And 1 over 10 to the positive third is 1 over 1,000. And so 1 over 1,000 is equal to x minus 4. If we add 4 to both sides, we get x is equal to 4.001 would be one way to express that solution. 4 and 1,000. All right. Next example, we've got the natural log of 2 minus x equates to 5. Again, we'll rewrite to start. Our base is e. It won't show up. Okay. But we know that e to the 5th, which is a number, it's a constant, is equal to 2 minus x. Now, if I wanted to solve for x, I could add x to both sides. I could subtract e to the 5th, and I would get x is equal to 2 take away e to the 5th. Now, you may not feel extremely comfortable working with that number, but believe it or not, you're done. You have a constant, nothing, an exact value. Nothing's been rounded. So we can leave it as 2 minus e to the 5th. If you really wanted to find an approximation, you could punch it in and find a decimal approximation. But you should be starting to feel comfortable working with these types of numbers. Next, e to the 2nd is equal to 3x plus 1 would be an alternate way to express this. I'm trying to solve for x. I'll subtract 1 and divide the whole thing by 3. I'm going to skip those steps because I don't have a ton of room in terms of writing them, but we would end up with, let's see, e to the 2nd minus 1 all divided by 3 is equal to x. Again, this is an exact value. Nothing has been rounded. You should be feeling pretty comfortable with that. Leave it. Be happy with it. If you wanted to get an approximation by typing it in, you'd of course need to wrap your numerator in a pair of parentheses when punching that in. Next, a couple rules for you here. First of all, the log of 10 to the n is equal to n for all n. That'll always be true. Okay? And 10 to the log of n, your second rule, and I'm asking that you read section 5.1 carefully, but 10 to the log of n will equate to n for all n greater than 0. We'll talk about the domain of the logarithm function next time we meet, but for now, know that you cannot take the log of a number less than or equal to 0, and so this rule right here only fits when n is greater than 0. Okay? But you can think of these functions as being inverses of one another. So if I wanted to evaluate the log of 10 cubed, or for example, if I wanted to say, well, first of all, the shortcut we know, the log of 10 cubed should equate to 3, but let's talk about why that's true. What if I wrote this initially as the log of 10 cubed is equal to x? So instead of having a blank space, I would have had an x, and I'm solving for x. Well, based on the prior slide, we know that I can rewrite this. There's my unknown base of 10, or my unwritten, I should say, base of 10. I can rewrite this as 10 to the x is equal to 10 to the third. And now I hope it's jumping out that if that's true, then x is going to have to equal 3, and so x is 3. How about the log of the square root of 10? Well, if the log of the square root of 10 were to be rewritten, we could rewrite that as log of 10 to the 1/2, because the square root is the same as the 1/2 power. And now what I hope you see is you have the log of 10 to the n, where n is a half, and so the log of 10 to the 1/2 is going to have to equal 1/2. Now, this rule here goes for natural logs as well. Okay? And so we can say that the natural log of e to the n is n for all n, and the natural log, or e to the natural log of n is n as long as n is greater than 0, because again, you cannot take the natural log of a number less than or equal to 0. And so if I'm trying to find the natural log of e squared times e to the n plus 3, I'm going to want to clean this up first. So I'll say this is equal to x. It's unknown. We're asking what it is. We want to find it. Well, I want to clean up what's inside the parentheses first. You have two numbers of the same base. Let's go back to our exponent rules. When you multiply two numbers of the same base, you're going to add your exponents. So I could rewrite this as the natural log of e to the, let's see, 2 plus n plus 3 is equal to x. Well, 2 plus n plus 3 is n plus 5, so we've got the natural log of e to the n plus 5 is equal to x. The natural log of e to the n plus 5 is n plus 5, so x must be n plus 5. Next example, natural log of 1 over e squared. Well, we could rewrite this, if I'm saying, hey, I don't know what that is, it's equal to x, find x, we could rewrite this as the natural log of e to the negative second. Now it's in the format that we want, because we want something like this, okay? And so I've got the natural log of e to the negative second is equal to unknown x. Well, x is going to have to equal negative 2. Okay? Last but not least, rewrite this, and I apologize, I don't have a ton of room here. Natural log of 1 over the cubed root of e, think about it, exponent rules. Pause maybe and think about how you could rewrite that. Okay, so we could rewrite that as the natural log of, jump the line, change the sign, e to the negative 1/3. And the natural log of e to the negative 1/3 reduces to just negative 1 over 3, based on these rules up here, based on this rule. All right, let's look at a couple more examples. And we're going to take it a step further. The next big rule, and this is probably the key rule for logarithms and natural logarithms that we'll use throughout Chapter 5 and beyond, is that the log of some base raised to an unknown t can be expressed additionally as t times the log of b. In other words, we can pull that exponent out in front of the logarithm. Same goes for natural logs. The natural log of b to the t can be expressed as t times the natural log of b. It can be pulled out in front. Now, keep in mind that we want to use exact values whenever possible. Let's take a look at this first example. Unless otherwise expressed. Solve for exact values. So 48 is equal to 7 to the x. Well, if you think about the previous examples, we had a logarithm or a natural logarithm showing up in the expression in all of them. In this case, we don't. When you don't know your exponent, that indicates, that should signal that you need to use a logarithm. And you can use a natural logarithm as well, but generally speaking, if the base is not e, I will be using in class, I'll be using a log instead of a natural log. But you can always use natural logs as well. We'll talk about that more in class. So I don't know my exponent. In this case, I don't know my exponent. In this case, I don't know my exponent. In this case, I don't know my exponent. That signifies, that should indicate use a log or a natural log. I'm going to use logs here. So I'll hit both sides with a log, which puts me here. Log of 48 is equal to the log of 7 to the x. Now, based on this rule, I can pull my unknown x out in front of the expression. I can say the log of 48 is equal to x times the log of 7. Now, the log of 48, think about that for a moment. The log of 48 it's a number. And the log of 7 is also a number. They're constants. If I punch the log of 48 into my calculator, I can get a decimal approximation, but right now this is an exact value. It's a constant. And so let's leave it as an exact value. Think of this as if we have some number equals some unknown multiplied by another number. Well, how would you solve that? You should just divide by both sides by the log of 7, which is a number. Okay? And we get we get x is equal to, so that reduces to 1, the log of 48 over the log of 7. Now, leave that. And one thing I want to point out is that this is not equal to, absolutely not equal to the log of 48 over 7. It does not work that way. Okay? In other words, the log of a divided by the log of b is not the log of a divided by b. So keep that in mind. You're done. You're finished right here. Now, if you wanted to get a decimal approximation, you could punch that in, but make sure that you wrap that 48 and close that off, for example, and then wrap that 7 as well. Let's look at another example. Jump down here. So here we have 48 is equal to 3 times 7 to the x. I've multiplied by a 3 out in front now, and so there's just one adjustment that needs to take place. The first thing we'll do before using logarithms is divide by 3. Divide both sides by 3, and so we get 16 is equal to 7 to the x. Now, it's when you get here, as a general rule, It's when you get here that you'll use logarithms. Again, the indicator that you need to use a log is the fact that you don't know your exponent. So I'll hit both sides with a log. Log of 16 is equal to, I'm going to skip a step, x times the log of 7. Okay? Divide both sides by the log of 7. Divide both sides by the log of 7. And I get x is equal to the log of 16 over the log of 7. Again, leave it. And this is not equal to the log of 16 over 7. All right. These next two examples, notice the base is e. The base is not something other than e. And so in this case, you want to use natural logs. Okay. Step one on this third example, we're ready. We've got alpha is equal to e to the t. Over here, we knew we were ready because we had alpha is equal to beta to the t. Okay. That's when you're ready to use a log as a general rule. You could have used it before, but you're adding steps. We'll talk about that some in class. Adding steps if you do that. So here I'm ready for a natural log. I'll take the natural log of both sides. Okay. And we know that the natural log of 100 is just it's a constant. Okay. Remember, a log and a natural log is an exponent. So this thing actually represents an exponent. It represents the exponent that you would raise e to get 100. Over here, we've got the natural log of e to the x. Now, based on prior conversation in this video, the natural log of e to the x is just x. And so x is equal to the natural log of 100. That's exact. Nothing's been rounded. If you wanted to round, you could, and get a decimal approximation, you could type it into your calculator. We're adding one layer here. Before I'm ready to take a natural log, the layer I'm adding is I'm multiplying by 20. So before taking natural log, I'll divide both sides by 20. 100 divided by 20 is 5. 5 is equal to e to the 3x. Now we're ready for natural logs. Again, I'm using a natural log because my base is e. So the natural log of 5 is equal to the natural log of e to the 3x. Well, the natural log of e to the 3x is 3x. And so 3x is equal to the natural log of 5. This is exact. Nothing's been rounded. We have one more step. We need to divide both sides by 3. Divide both sides by 3. And so our x value, our unknown x, is the natural log of 5 divided by 3. Again, I just want to point out this is not equal to the natural log of 5 over 3. They are not equal. Okay? The natural log of 5 is a constant. Divide that constant by 3, and you have your answer. We'll close with a couple more examples. And I know this is a long video, but this is a challenging concept that hopefully is making sense. I want to say that we're going to use these skills that we've been working through in this video in real-world problems next time that I see you in class, in real-world context. Okay? I want to solve for t, and there's a whole bunch of different variables here. Everything is a constant, a, e, b, and g, except for t. T is my unknown. Think of it as x. It's my independent variable. Okay? And I want to solve for x. Well, I don't know my exponent, and so that tells me I'm going to have to use logs or natural logs eventually. I also have a base of e, so that should indicate, hey, use a natural log instead of a log. And I've got this a being multiplied out in front, so I need to get rid of that first before I take the natural log, or at least you don't have to. I suggest that you do. We'll talk about other ways around that in class later. But for now, I'm going to divide both sides by a. Divide both sides by a. I'll rewrite e to the bt is equal to g over a. Now, g is a constant, a is a constant, so g over a is a constant. We are now ready for natural logs. I'll hit both sides with a natural log. Okay. The natural log of e to the bt is bt. bt is equal to the natural log of g over a. I'll divide both sides by b, and I have solved for t. Okay. Next example. I'm actually going to jump down to number 3 first, and then I'll come back to 2. So next example. Notice that we're back to kind of the beginning of this video. The logarithm shows up in this expression. So I need to rewrite. It's going to require a rewrite first. My rewrite is e squared, which is a constant, is equal to, let's see, 10 to the 2x minus 3. Okay. Now, this one a little complicated. I'm laughing because when I wrote the problem, I wasn't thinking it was quite this complicated, but now I'm looking at it, and we're going to have to, let's see. You know what? My error. Let's go back. There's an easier way to do this, and maybe you recognize that. The log of 10 to the 2x minus 3 is what? Think about it. The log of 10 to the 2x minus 3 is 2x minus 3. Okay, remember the log of 10 to the n is equal to n. So that simplifies things a great deal. So I'm just going to rewrite that left side as 2x minus 3. In this case, that's equal to 2. Again, I didn't have to do anything here except use that rule that we talked about earlier. And if I want to solve for x, I'll add 3. That gives me 5 over here is equal to 2x. I'll divide both sides by 2, and x equates to 5 halves, or 2.5. So not nearly as ugly as initially I mentioned. All right, back to number 2. So we want to solve for our unknown, and our unknown is part of the exponent. And so that indicates that we need to use logarithms. But before we do, let's divide both sides by 10,000. Divide both sides by 10,000. And that puts me here. 1/2 to the t over 3 is equal to 1/10. Now, my base is not an e. My base is not an e. It's a 1/2. So I'm just going to suggest that we use a logarithm. Keep in mind that the log of 1/10 is a constant. Leave it that way. It's exact. Nothing's been rounded. Okay? When you take the log of a base raised to a power, again, you can pull that exponent out in front. And so that leaves us with t over 3 times the log of 1/2 is equal to the log of 1/10. Now, I want to isolate t. That's been the goal all along. Isolate t. Well, in order to isolate t, I'll multiply by 3, and I'll divide by the constant log of 1/2. And so that leaves us with t is equal to 3 times the log of 1/10 over the log of 1/2. So again, you have a couple things I'd like you to do for the homework assignment. If we go back to the very first slide, read section 5.1 carefully. I covered the vast majority of it, but I'd like you to read it. You need to read it. Well, and then you've watched this video. If you feel like you need to watch it again or parts of it again, do so. And then start working on homework 12, which is 5.1 in Chapter 5 skills. You have most of what you need to be able to complete that assignment. And the next time that I see you, I will answer any homework questions that you have. Be sure to post those on As You Learn. Take care.